We're Lydia and Catherine, and we're PhD students working with plasma. So you might be wondering, what is a plasma? Let's take a cube of ice. Now, if we heat up a cube of ice, we're also giving it a bit of extra energy. And when we give the cube of ice that energy in form of heat, we get water. And if we put a little bit more energy, we get steam. But what happens if we put a little bit more energy? Well, when you add even more energy to a gas, you get a plasma. Plasma is actually the most common form of matter in the universe, but it exists mostly in space. Here on Earth, the most common form of plasma we see is lightning. Now let's get back to our example of ice and water. Water is made up of 2 hydrogen atoms and 1 oxygen atom. Within each atom, you find what we call subatomic particles. These are neutral neutrons and positive protons that we tend to find in the nucleus, and negative electrons. If we give our molecule lots and lots of energy, the electrons will actually break away from the atom, meaning that the electrons will be a separate negative ion, and the nucleus will be a separate positive ion. So, although a plasma has an overall neutral charge, it's actually made up of separate positively charged ions and negatively charged ions flying around. These electrons are constantly falling back into the nuclei before being thrown off again, which releases energy as radiation. We can see this here as visible light, although there's also ultraviolet radiation that we can't see. The charged particles of a plasma are also unstable and want to try to become neutral again, so try to react with each other or other particles the plasma comes in contact with. These features make plasma a really useful substance for us to use. Here we use it for something called surface energy modification. Have you ever noticed that water boils up on some surfaces but spreads out more on others? This is due to surface energy. The plasma we use makes the surfaces hydrophilic, or water-loving, which means the water spreads out more. This happens because the electrons in the plasma bump into the bonds on the surface of the glass here and breaks them apart, which produces what we call polar surface groups, with different charges at the base and the tip. The charge of the tip attracts the water molecules, which are also polar, and causes the water to spread out across the surface. Plasma is also great at cleaning. What might look clean to you or I is actually covered in tiny particles of dirt and dust, usually oils from our fingers, which can also affect surface energy. Reactive species and radiation in the plasma can break apart these particles and remove them from the surface. This can be beneficial for lots of applications. Here at Cranfield for our PhDs, we're working on using plasma for surface energy modification for different applications. So for me, my application is aerospace. I want to make aeroplanes lighter and stronger, and to do that I use these. These are composites. So they're 2 or more materials, usually carbon fibre and a type of plastic, and this is fiberglass. And we can use plasma to make them more sticky. And for Catherine's project,
I'm using plasma to increase the wettability of mirrors that they use in concentrating solar plants, which are typically located in the desert where there's lots of sunlight. It also means they get covered in sand and dust and they have to be washed regularly. But washing uses huge amounts of water, which in the desert is already a really precious resource. So plasma can help to increase the wettability of the surface, which means you need less water to do the same amount of washing, which is really beneficial.
in our work, we take either argon or nitrogen gas and create what we call a non-thermal plasma. This means that the energy of the plasma is mostly in the electrons, not the heavier ions. It's also low temperature, related to other plasmas, although it's still pretty hot to us. Here you can see we've put a mask over our sample. This is what us scientists use when we want to only selectively treat certain parts of the sample. Now, when we take the sample out, you can't really see the changes to the surface, but let's spray it with some water. Can you see it? Okay, now let's try that again, but let's spray it with some ink. See? Here you can see that the areas that were exposed to the plasma have become more hydrophilic and pull the water in. Thank you for enjoying our short talk on surface energy modification by atmospheric pressure plasma. We'd like to thank everyone at Cambridge Science Festival for giving this opportunity, and I hope you enjoy the rest of your festival.